You've heard it a million times in science news, right? The results were statistically significant. And that significance, it almost always comes down to this one little thing called a p-value. So what in the world is it, really? Okay, let's spend the next few minutes and get this figured out once and for all.
To make sense of this, let's start with a really simple, practical question. Imagine we have two new drugs, drug A and drug B, and all we want to know is one of them actually better than the other?
So, we run the tiniest experiment possible. We give drug A to one person, and hey, they're cured. Awesome. We give drug B to another person, and they're not. So, can we stop right there? Can we declare drug A the winner?
Well, of course not. I mean, think about it. What if the result was just dumb luck? Maybe the person on drug B had some weird allergy, or they forgot to take a dose. Or maybe drug A doesn't actually do anything, and that one person was just cured by the placebo effect. There are just a ton of random things that can mess with our results in a tiny experiment.
Okay, so the obvious answer is we need more data. Let's test each drug on lots more people. But even when we do that, we're still stuck with the same fundamental problem. How do we know if the difference we're seeing is real or if it's still just, random noise?
Let's imagine one scenario. After testing on thousands of people, we see that drug A cured pretty much everybody, while drug B cured almost nobody. In this case, come on, it feels totally obvious, right? It would be crazy to think this was just random chance. The conclusion is a no-brainer.
But what if we get a result that looks more like this? Drug A cured 37% of people, drug B cured 31%. I mean, yeah, 37 is bigger than 31. But is that 6% difference really big enough to mean something? Or could that tiny gap just be a fluke from all that random chaos we talked about?
And this, right here, is the central problem. How do we draw a line in the sand? How do we make the call and decide if a difference is real or if it's just statistical static? Well, this is the exact job the p-value was invented to do.
So how do we solve this? With the p-value. You can think of it as a kind of randomness detector, or a flukometer. It just spits out a number between 0 and 1 that tells us how confident we should be that the difference we saw isn't just a coincidence.
And the rule for reading them is super simple. Smaller is better. A p-value that's really, really close to 0 is basically the math screaming at you, hey, it would be super weird to get this result if it were just random chance, and that's what gives us confidence that the difference is probably real.
So, how small is small enough? Well, in practice, the most common threshold used across a ton of scientific fields is 0.05. If your p-value comes out less than 0.05, you usually get to say your result is statistically significant.
Okay, now the formal definition of this is a famous head-scratcher, so let's just walk through it together. A threshold of 0.05 means this. If the two drugs were actually identical and we ran the same experiment a bunch of times, then we would expect to see a result this extreme just by random luck only 5% of the time. It's really about setting an acceptable rate for being fooled by randomness.
Let's make that really, really clear. Imagine we run a test where we know there's no difference. We just give drug A to group 1, and we also give drug A to group 2. Most of the time, the results are going to be pretty similar, and you'll get a big, boring p-value like 0.90, which correctly tells you, yep, nothing to see here, folks.
Most of the time, yeah, you'd get that big p-value. But every once in a while, pure random chance is going to throw you a serious curveball. For instance, one group might just happen to get all the people with really strong placebo responses, and the other group might randomly get all the folks with rare allergies. All of a sudden, the results are going to look totally different, and you could get a misleadingly tiny p-value like 0.01, even though you know for a fact the drugs were identical. And that right there, that has a name. It's called a false positive. We saw a small p-value, and we concluded there was a real difference, when in fact, there wasn't one. It was all just a random fluke.
So here's the crucial point. When we use that 0.05 threshold, we are explicitly making a deal with ourselves. We are accepting that 5% of the time, or in 1 out of every 20 experiments where there's actually no real effect, we will get tricked by randomness into thinking we found something real.
So we get the 5% error rate. But understanding that leads us to the single most important and honestly the most misunderstood part of what a p-value does and what it absolutely does not do.
Okay, just look at these two experiments. In the first one, we saw that 6% difference, remember? But the p-value was 0.24, so not significant. Now look at experiment 2. This time, with a massive number of people, we only see a tiny 1% difference. But because our sample size is so huge, the p-value is 0.04. That is statistically significant.
And that is the critical takeaway. A p-value tells you how certain you are of an effect, not how big the effect is. You can be very, very confident that you found a very, very tiny difference. Statistical significance does not always mean practical, real-world significance.
So let's recap the 3 big takeaways. 1. A p-value is just a tool to measure our confidence against random chance. 2. A p-value less than 0.05 is the common but not absolute rule for calling the result statistically significant. And 3. The most important catch of all. It tells you about confidence, not about importance or the size of the effect.
Which leaves us with one final thought. The next time you see a headline that says a result is statistically significant, you now know the very first and most important question you should ask is, okay, but how big is the effect?